Okay, I think you can see my screen now, right? Okay, fine.
Yes,
Yes. So today we will talk about a very important thing. We will talk about the resistance. Okay. So in the last lecture we talked about the distributed elements, and the lumped elements. Okay. You know what is the difference. So we will usually use the distributed theory. Actually, everything is distributed. You cannot see something, you cannot confine at some point. Everything is distributed. Usually this theory at high frequency we will use, and we will usually use the field theory. That means you know electromagnetic field theory. But in the lumped circuits, if we consider our resistance, our inductance, everything is concentrated at one point, or we can make them concentrated at one point. Suppose if you take a piece of wire, it is having actually a distributed nature. But if we are passing low frequency, we can assume that the total wire, the resistance of the total wire at some point, we can say it is a lumped elements. We can model it like a lumped elements. So the lumped, if we assume the lumped assumption, usually we will use at a low frequency, and we will use the network theory. And this course is about the electric circuit theory, or we can say it is network theory. We will usually use the write like this, network. So we will usually use electric circuit theory. You can say electric circuit theory. That is our course, right? So we will talk about the lumped elements. Okay. So if you have a wire, a wire with a bulb, you can say that this wire is having, suppose this is the resistance of the wire, 10 ohms, and maybe the resistance of the bulb maybe uh, some 15 ohms, and you are giving a DC power supply, something like this. You know this is positive and negative. You can model this like this also. There is a 10 ohm, there is a 15 ohm, and you have something like this. Okay. So what is the resistance here for the wire? The connecting wires have the resistance equal to 0, and yes, we will assume it as 0, and we will model everything. All this wire resistance Rw is here and Rb is here. That means we are concentrating everything at some points. This modeling we will call, this is known as the lumped assumption, okay, or lumped modeling, okay, assumption. We are assuming like this, but this is valid only for low frequency. When you move towards 100 megahertz or 1000 megahertz, this is not possible. You have to use electromagnetic field theory. So we will, in this course, we will usually consider the low frequencies, DC and AC with low frequency. But if we are studying high frequency case like more than 1 megahertz, like 10 megahertz, 100 megahertz, we need another theory that is known as electromagnetic field theory or transmission line theory. There is a lot of things. It is a separate course. So today we will first talk about the resistor. And you know, this is the notation for the resistor, and the unit of the resistance is ohms. Okay, and usually represent like this symbol. And you know that the relation between the voltage and the current, we have studied already the Ohm's law. We have already studied the Ohm's law, because it is nothing but V equal to I into R, right? Or I can say my I is equal to V over R. This is equal to, we can write in another way, 1 over R into V. And you can write this 1 over R has something different, another notation, which is G. We will call this guy actually conductance. We will call conductance, and the unit is just, you can see G equal to 1 over R. It is 1 over R. Yes, it is having Siemens. We will also usually write this has, it is, this one is ohms. You can see this is ohms, but this is mho. Okay, this is another way to write it. And you know that if you take a piece of, if you apply a voltage, usually the resistance is denoted like this. This is R. Okay, now if you take a piece of wire, if you take a piece of wire, you can model the resistance. Suppose this is the area of the cross section. If you take the area of the cross section, this is say S. If this is having a length of L, and if it is having a property which is nothing but the resistivity, I have already told you this thing, resistivity, which is usually represented as rho, then the resistance of this element is defined as uh, rho into L by S. We have already seen this thing, okay, in the last in the last week, I think so. Yes. Now we are talking about the lumped elements. You have a voltage source and you have a resistance here. Then you can see that the electrons will flow like this. It will start moving like this. It will start moving like this. This is the movement of electron. Or we can say that the actual direction of the current will be from positive to negative, right? It will be from positive to negative. So the current will be moving like this. Okay, the current will be moving like this, and you can say this is the resistance. So we have a current I and you have a voltage source. Okay, you have a voltage source. Now I will tell you what is happening in electric field terms. Okay, suppose you have the same circuit. Now I will just make it little bit bigger. You have a wire or something having something like this. This is your resistance, R, the same thing. Okay, same. And you have something like this. You know that this is positive and this is negative. You know always the electric field inside the battery. Electric field inside the battery, actually electric field, direction of electric field, you know, if you have a positive charge and a negative charge, this is the direction of the electric field. So you have a positive polarity here and you have a negative here. So the direction of the electric field inside the battery will be like this. Got it?
Yes,
Yes.
Gupta.
Yes. So since the current flows, you can see the current will be flowing like this, I. It will be flowing like this. So there will be definitely the energy will be dropping because this guy resistance will take some energy. So energy will be dropping. So you can say that this end, the current will be entering, the energy will be dropping. Okay, so energy will be going down and this is negative, right? So the direction of the electric field will be from positive to negative, and you have the current here. So the current is like this, the current is going down. Okay, like this. So this is the current. Okay, I'm just representing. This is I. Now, so this is the basic circuit that we can say. So inside the battery, the electric field is like this. Now, I didn't teach you anything about the Kirchhoff law, but I'm going to apply some ideas now to demonstrate. But we will come in detail to the Kirchhoff law later. Now you can see I am starting from this point. I am starting from here. Now you can see, since I am starting from here, you can see the electric field is coming downwards, right? Am I correct? It is going down, right? Now, yes, I am moving in this direction, clockwise. I am moving in this clockwise direction. So if I move in clockwise direction, whether I am going in the direction of electric field or opposite to the direction of electric field, in which direction I am going actually, if I move in clockwise? Opposite. So I am just writing this as some voltage, let's say V. Okay, you can say V. Now, since I am moving opposite, I will just assume a sign of negative. Okay, so I will just assume this is minus V. Now, you can see if I reach this point, reach here, now you can see the electric field is going down, right? And I am moving exactly in the direction of electric field. If I am saying about this guy R, am I correct? I am moving in the direction of electric field. Is it correct?
Yes.
Yes. If I move in the direction of electric field, I can say that I will assume positive sign. Okay, I will assume, because I already assumed that if I move opposite direction, I assume negative. So it is reasonable that I have to assume positive sign if I am moving in the direction of the electric field. So plus you have this, how much voltage drop is there across the resistance? It is nothing but I into R, right? You know this thing because we have already seen the Ohm's law in the previous lectures. So this total, we will say it is zero, that is the Kirchhoff law, or we can say that the voltage V equal to I into R. So what is this voltage? So this voltage is nothing but the voltage drop across the resistance. So the voltage drop across the resistance will be something like this. The voltage drop here will be I into R. So we have the formula V equal to IR, okay, from this. Okay, so I hope that this is clear to you. Okay, now this resistance, the element resistance that we are talking about now, the element resistance, this element is the resistance of a material will never change, but it will change at some point. When it will change, what is your, whether it will change or not? Suppose if you are taking a piece of wire and it is having a resistance of 10 ohms, will it change? Will it change or not? Please give me an answer.
The resistivity.
Hmm?
No, except if the resistor damage.
If the resistor damage, not no, okay, if the resistor damage, definitely it will change, of course. But will it change?
But in the normal
No,
situation, no.
No, it will not.
not
How?
change.
With DC, no.
Yeah, it will not change. But
Sure,
it
you
will
mean the
not
resistivity
change.
or what?
Yes, resistivity. If the resistivity changes, you know this equation, rho into L over S. If this guy resistivity changes, the resistor will change. Resistance will change, right? So
Right.
yes. Now it will not change if the temperature doesn't change, right? You have to be very careful about this. If the temperature changes, the resistance will change. So if the temperature increases, so if you have a piece of wire and it is having an area like this S, yes, and it is having a length L, and it is having a property rho. When the temperature increases, what will happen?
Decrease of
Resistance
resistivity.
decrease.
Is it decrease
Resistance
or
decrease.
Increase, it will increase.
the resistance will increase? Why it is increasing?
Increase.
Because
Because the
the
resistivity
resistance,
will increase.
yes, if the temperature increases, the resistivity will increase. Then what will happen? The resistance will increase. And there is a canon for this. You can say the resistance at a temperature T is equal to resistance at 0 degree Celsius into 1 plus alpha T. Okay, this is how it is changing. It is almost a linear relationship, but actually this is an approximation. But why the resistivity changes? Anybody, please, can you answer me? Why the resistivity changes?
Because the free electrons.
Hmm? Because
Because the free electrons.
is not clear. I think your voice is.
Because the free electrons.
Yes, it is free electrons. More free electrons will come, but what is happening? Even though more free electrons are there, actually, you know that if more free electrons are there, then it is easy to have more current, right?
Yes, but
But
the electrons.
I am saying,
each
yes, these electrons will be moving randomly and they will collide, they will hit themselves. So you can see that two neighboring electrons will collide, so that the total speed of the electron through the conductor will reduce. You understood? Do you remember I
yes.
talked about the speed of the electron, drift velocity? You remember?
Yes, Doctor.
Yes, I will talk about this thing. Okay, when the temperature increases, the speed of the electron, the drift velocity will decrease, so that the resistivity will increase and it will lead to increase in the resistance. Okay, this is the reason, and this is the Qanun. I hope that this is clear. Okay.
The drift
Now,
velocity, Doctor, will decrease.
yes, it is because electrons
Why?
will, you see, why? Because there are, you see here, you are always, you may be driving through Aba Khamis Road, right? Okay.
Yes.
Now,
Yes.
please don't, okay, yeah. If in the morning at 7 o'clock, you know what is the traffic, how many cars will be there on the road? Lot of cars,
Right.
right? Then you have to automatically decrease your speed, right?
Right.
You cannot go much fast, right? If the traffic is too heavy like this, more electrons will be there and all these electrons will be moving in random direction. So the total drift speed will become reduced. Is it clear? Logical?
Yeah.
Okay.
Yes.
I hope that, yes, like that.
Doctor,
Okay, you can imagine like
the
this.
speed will be the movement of electron will be randomly,
Yes.
or because of the voltage it will be straight.
No. Electrons will be moving, but they will randomly moving in to and fro in different direction, so that the actual effect due to the voltage will reduce actually. Even though if you apply 10 volt, if you apply 10 volt at a temperature or a higher temperature, then what will happen is that lot of electrons will be moving in random direction due to the temperature, so that the smooth movement of the electron will not be possible. So that we can say the drift velocity will reduce and it will increase. We can say that the resistivity will increase. Okay, is it clear?
Okay. Yes, Doctor.
Yeah. Now we will see what is power. Can you tell me what is power?
The work done per unit second,
Yes.
per unit time.
Yes. Power is nothing but work done by time, right? Or we can say that it is nothing but amount of work done in unit time, dW over dt, right? Means this W is nothing but the work, okay, and this is nothing but the time. Is it correct? So we can say that the power P is equal to dW over dt, which is nothing but, we will make something like this. It is nothing but dW over dQ into dQ by dt. Is it okay to write like this? Multiplied?
This is
Yes,
the
Doctor.
voltage multiplied
Yes, it's
with
correct.
current.
Voltage multiplied
Yes.
current.
It is the work by charge. It is the amount of work done by unit charge multiplied by amount of charge flowing in 1 second or time. So what is this work by charge? You know that amount of work done by unit positive charge or unit charge is nothing but the voltage, right? And amount of charge flowing in 1 second, you can say this is nothing but the current. Am I correct? So you can say that it is nothing but voltage into current. Is it clear? So the power is nothing but the voltage into current. So in the case of resistance, in case of our R, you know that the power is equal to voltage into current, and you know this voltage is equal to I into R. In case of this guy, okay, this circuit, you can say the amount of voltage that it is dropping across the resistance, you can say this is the current I. So if I substitute P equal to, I am going to substitute this equation 2 in 1. Okay, I'm going to substitute 2 in 1. Yes, then it will become this I into R into I. That means it become I square R. So this is one equation for the power across a resistance. So the power across a resistance. Okay, then what is the energy? Okay, energy I will, okay, sorry. I can also write this in another way. We have the equation P equal to voltage into current. I can write the voltage. I can write the current. What is the current? This is voltage into what is current? Current is equal to V over. So this is also V square over R. So the power across a resistance, you can have the power across a resistance, you can have I square into R, or another formula V square over R. Okay, you can use any of this to calculate the power according to your convenience. Now we will see what is energy. Okay, energy, and what is the unit of power? I forgot to tell you the unit of power. It's watts. Watts is nothing but joules per second. Okay, joules is the unit of energy. So energy, the unit of energy is joules. So you know that power is equal to dW by dt, and this is the work done, and you know this is work done is nothing but the energy. Okay, it is the work done by the charge actually. So it is nothing but the energy. So I can write this dW, a small portion of the W, as power into dt. So you can find out W as integral of minus infinity to t p dt. Why I am taking minus infinity? Anybody? Anybody, please?
Get 0 to t, doctor.
It is not 0 to t. Minus infinity means, suppose you have a bulb which has turned on maybe before 100 years, for example, just not 100 years anyway, maybe 100 days, and you are looking at this time t. Currently, suppose you have a bulb like this, you have a bulb, switch on, I can say maybe on January 1, and the time has passed. This is the time, and you came here and see the bulb at time t. And what is this time t? And you are at time t maybe after some 100 hours. Then you have to integrate this time up to this time t. Okay, so you have to integrate throughout this portion. That's what the meaning. So you will ideally take from minus infinity to the time that you are looking at. Okay, is it clear?
Yes.
Yes, doctor.
Yes. Now we can say something like this. So the power, okay, for in the case of resistance, energy, in the case of resistance, you know that the power is equal to I square R, or
Excuse me, doctor.
Yes. Yes.
The integral, will we take always minus infinity or the initial value of time?
You don't know. Actually, this is ideally we can speak like minus infinity, but actually, if you know the initial value of time, you can start from the initial value of time. Okay, that's fine.
Okay.
But when we define something, we will always say like that. Okay, because we cannot ignore any chance. Okay, we cannot ignore any chance. Okay, that's why we start from minus infinity. Now, what is this? The power. So sorry, the energy or the work done, we can say, is nothing but integral minus infinity to t. You know this is I square r. If you know the current as a function of time, you can say it is I square r into dt. Okay, or you can say like this, if the current is a function of time minus infinity to t, if the voltage is a function of time, then v square t by r dt. So these are the two equations to calculate the energy. Have you noticed something? In the equation of the energy, you can see the integral. You can see the integral minus infinity to t. That means the energy drop across a resistance will depend on all the previous time. So the energy consumed, okay, energy consumed by the resistance will depend on the current or voltage. It will depend upon the current or voltage in all the previous time. That's why we integrate from minus infinity to infinity. So it will, the total energy consumed by the resistance will be depending upon all the previous time, okay. Have you understood this point, what I'm saying? Is it clear?
Yes, Doctor.
Yes. Now we will see what is the VI characteristics of this resistance. Okay, characteristics of the resistance. You know that I can draw the VI characteristics in two different ways, but I will use the I in x-axis. I can use in another way also, there is no problem. But this is for my convenience. This is the voltage drop. And you know that V equal to I into R, right? So it will be a straight line. It is passing through the origin. Why it is passing through the origin? Because when current equal to 0, voltage is equal to 0. And the slope of this line is equal to, how much it will be the slope?
R.
Yes, the slope will be R. But if I draw like this is voltage and this is current. In another way, I can draw like this. The slope will be 1 over R. Okay, this is another way. Now you can see the quadrants. Which is the first quadrant? This is the first quadrant. This is the second quadrant. This is the third quadrant. This is the fourth quadrant. Okay. Now, if you find the slope at any point like this, you can find the slope at any point. So this is delta V. Okay. And this is delta I. Then the slope is nothing but delta V by delta I. Okay. That is equal to R. Okay. Now, this is the fourth quadrant. You can see that when the voltage, when the current is negative, this is minus I and this is minus. When the voltage is positive, you can see the current is also positive. When the voltage is negative, you can see that the current is also negative. And you can also see that this equation, this is a straight line. This is a straight line. So it is a straight line. The curve is a straight line. That means your resistive network is linear. Actually, it is linear. Okay, this is linear. You can say that your network is linear. You can say. You understood the point what I'm saying? It's clear.
Yeah.
Yes, doctor.
So when the voltage is positive, current is positive. Okay. That means when the voltage increases, the current increases proportionally. When the voltage decreases, the current decreases proportionally. So this has lot of points I want to say. You can say this. One point is it is linear. Okay. Then you know that this is passive. Have you heard about this term, passive? Because passive means it consumes the energy. When the current flows through the resistance, it consumes the energy, it eats the energy. Okay. And it is passive. It cannot produce the energy, or it cannot convert the energy from one form to another form. It simply eats the energy. That's why it is passive. Then another term, it is bilateral. It is bilateral means it is having, this is I, this is V. It is having the property on both sides. That means if you give positive V, you are getting positive I. If you give negative V, you are getting negative I. Okay. That means it will bi. You know, bi means two. Okay. So it is having two properties. That means it is having the property in the first quadrant and in the third quadrant. Is it clear?
Yes, doctor. Yes.
Yes.
Yes, doctor.
Also, it is time invariant. This property, this is the property. This is I, this is V, and the slope is R. This property will never change if the temperature is constant. I am talking about the temperature is constant. If the temperature is constant, this property will never change. The slope of this curve will be always the same. Whatever voltage you give, whatever current you give, the slope will be same. So resistance, you have a formula for resistance is V over I. It doesn't mean that the resistance is depending upon the voltage. Resistance is the property of the material. It is the property of the material. But this formula is just for calculation, Okay, it is having some dependent relation. That's why it is the property of material actually. So don't think that the resistance is the property of voltage and current. It is not the property of the voltage and current. Even though the Qanun is showing V over I, it is not the property of the voltage and current. It is the property of the material. And the resistance formula V over I is actually meant for calculation. This is how you can calculate. Is it clear to you?
Yes.
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 So yes. So this is the.
So we can't.
Yeah.
We can't use this formula to calculate the resistance.
We can use the formula for calculating the resistance, but we should understand that it is not actually the property of voltage or current. It is the property of that material. Okay. That's it.
Material. Yes.
Yeah, it is a property of the material. Don't think that it is the property of the voltage and current. Even though the formula contains voltage and current, it is not the property of the voltage and current. It is the property of that material. But if you calculate voltage over current, it will give you the value of resistance. It is just giving the value of resistance. Okay, it's clear? I hope that it is clear to you, right? Now we will see something very interesting, which is known as the inductance. Inductance is the property of the material, actually usually denoted as L. Okay, and if you give a voltage, suppose you have a, okay, you can say this is the L, usually represented like this. Okay, and the voltage across this is V. Okay, and you can mark like this L, and suppose some current is flowing, this is I. Okay, this is some current I. Now when the time varying current is flowing through the coil, then time varying magnetic field will be produced. I told you, when the current flow through the coil or any wire, there will be magnetic field. If the current is also changing with time, then it will cause the time varying. So the time varying or time varying means if there is a current which is changing with time, if time varying current will produce a time varying, it will produce a time varying magnetic field also. Magnetic field. We are not talking about the electric field because we are talking about the lumped elements. Electric field will be negligibly small at low frequency anyway. So because of this, whenever there is a time varying magnetic field, you know that there is a coil and there is a current. Suppose there is a current which is coming, and if the current is moving like this, and if the current is moving in this way, okay, if the current is moving like this, I think you can understand which direction the current is moving, just like the clockwise I am saying. Okay, just I am saying like a clockwise direction. If the current is moving in the clockwise direction, downwards, actually you can say it is clockwise direction, then definitely there will be a magnetic flux. And what is this magnetic flux? Usually the magnetic flux is magnetic flux in each coil. Suppose if you take one coil like this, if you take one coil, there will be a magnetic flux, and it is usually denoted by phi, and the unit of this is Weber, usually denoted like this, Weber. If there are n coils, this is the first coil, this is the second coil, this is the third coil, like this. If there are n coils, then the total flux will be n into phi. N is the number of turns. Okay, n is the number of turns. So there will be magnetic field, and you know that according to the Lenz's law, a magnetic field will be produced inside the conductor to oppose the flux. So what will be the direction of the flux? Anybody please tell me whether the flux will be pointing down or pointing up. In this case,
We use
I think it's the
right
same
hand
as
rule.
current direction.
yes, we will use the right hand rule. So if you use the right hand rule, can you see my finger?
Yes, we can.
Yes, it will be going down. So the flux will be going down actually. If the flux goes down, if it is pointing downwards, this is the direction of the flux inside the coil. Or if the coil is wound around some material, this is the flux inside that material, which is, this is the direction. And if you see this arrow mark, it is pointing down, and this will be the north pole and the other end will be the south pole. Okay, this is by experimental observation. By experimental observation, I cannot prove it mathematically now. So it is by experimental observation. Okay, and this inductor don't like this change, so it will create an opposing force. Okay, whenever there is a current in the inductor, it will create a magnetic flux, and this magnetic flux are linked to the coil. If you take a one piece of this coil, you can see here there is a magnetic flux which is, sorry, the magnetic flux is going down. So current is moving like this. This is the direction of the current. Okay, this I am just elaborating this. Okay, so it is going down, and this doesn't like this. You can say that the magnetic flux is going down. Because of this, it will try to oppose the current. It will try to oppose the current by making a magnetic field in the other direction. It will try to make a magnetic field in the other direction. Because of this magnetic field, you know, this is the magnetic field, and this magnetic field is linked to this coil. Okay, this magnetic field is linked to this coil. This is the coil which is carrying current, but the magnetic field is linked to this coil. This coil is linked with the magnetic field, so it will try to make another current in the opposite direction to oppose it. You got the point what I'm saying? This is known as Lenz's law.
To oppose the change of the
Yeah,
current, right?
it will try to, because the actual direction of the current,
in the opposite direction.
yeah, it will try to create the current in the opposite direction. Okay, it will try to create the opposite direction whenever there is a change in the magnetic. Yeah, but
Yes.
this will happen only if there is a change in the magnetic field. You know that if the magnetic field is constant, any EMF, right? I will explain once again this thing. Suppose you have a magnetic field, this, and you have a coil.
Can you repeat what you said?
Okay, sorry. Suppose you see here, this is our direction of the magnetic. This is our north pole and this is the south pole. And our current was moving like this. Okay, our current was moving like this. Now, this is the current due to our voltage source. You can see I will apply a voltage source here. I will apply a voltage source here. This current is due to our voltage source. Okay, I will ask you one question. Is a function of time, or I can say if this current is AC, then what will happen to this magnetic field? This magnetic field also will be changing. Am I correct?
Yes.
If the current is changing, then
Yes.
changing. It is deep. Long time. There is AC current for a long time. Voice is, what is happening? I don't know. Okay.
I think
Is it okay now?
Now, yes.
Yeah. Okay. If this is a DC current, can you tell me whether the magnetic field will change?
No, it will not.
No, it will be constant.
It will be constant. Okay. Now, if this is a AC current, this flux also will be changing. This flux will be changing. There is no other doubt regarding this. The flux will be changing. Now, you know something from your high school that whenever there is a changing flux and a coil, then what will happen? If there is a changing flux, if you have a coil,
It will
you
be
put a
produced a
flux.
current.
Yes, if there is a flux which is going inside, you know that it will produce the current, right? It will produce the current or EMF. You can say it will give rise to the EMF, right?
Right.
yes, right.
Right. But if you give an DC, if you bring a DC voltage for a long time to a inductor, then what will happen? Whether the flux will be changing? Flux will not be changing, right?
Right.
Because it is DC. Then what will happen? If there is no flux, nobody, no current will be, no voltage will be induced, right?
Yes, sir.
Yes.
Right.
Yes. If there is no voltage induced, then the current which is opposing the original current, what it will be? Nobody will oppose, right?
zero.
Zero. So this current will be flowing as such. Nobody will oppose it, right? Nobody will oppose it. He will flow smoothly. Am I correct?
Yes, sir.
In the case of DC, for a long time. But if you give a AC signal, the situation is different. The flux is changing. When the flux is changing, immediately there will be a current which will be formed to oppose in this other direction, because this is the original direction of the current is like this. This is the original direction. You can see this is the original direction. This is the original direction. Original. Okay. So there will be a current which will try to, there will be a EMF which will make a current which will try to oppose the original current, and it will make another current, something like I dash T, to oppose the original current. So the net current will be I of T minus I dash T, right? So this is the situation. So the actual current during the always there will be somebody to oppose, and this is known as the Lenz's law. You have studied this Lenz's law. Okay, so this is the case of the inductor. So you know that whenever you give current, there will be flux around it, right? Whatever, if you give a DC current or AC current, there will be flux. So if you consider an inductor like this and you give a current, this is the I and this is I, which is flowing down in a clockwise direction down. Okay, then it will be producing a flux. It will be producing a flux, maybe time changing or constant. Anyway, it will be producing a flux which is equal to some psi. You know that this is psi is equal to n into phi, but this flux we can say in terms of current, like it is proportional to the current, right? If you increase the current, there will be more flux, right?
Right.
Yeah, that we know this. So we can say that this psi is equal to some constant into I. That's it. So this is known as this L is known as, this constant is known as the inductance. This is a property of that coil, inductance, and it will depend upon, definitely it will depend upon the number of turns. Okay. So this is the inductance parameter. We can say inductor parameter, inductance parameter of the coil, and the unit of this is Henry. The unit of this inductance is, the unit is Henry. Okay, or we simply write like this, H. Okay, so you know that this psi is equal to some L into I, and this is the flux. Whenever the flux changes, when do the flux changes? If you give the time changing current. So the psi at a function of t, you can say, whenever the current changes, the flux changes. So the rate of change of flux, I can define this by using the differentiation. The rate of change of flux, that is how much flux changes in unit time. That is, you can write like this, L into di by dt, right? So this rate of change of flux, if the amount of flux changes in unit time, that we will call as the voltage. So you can see the another thing for the voltage. So the voltage induced across the voltage across the inductance is nothing but the rate of change of flux. You can see, you can experimentally determine this fact. So you have now new formula, that is psi is equal to n into phi, and psi is equal to L into I, and d psi over dt is nothing but the voltage, which is nothing but L into di by dt. Definitely this is a function of time. The voltage is also the function of time, the current is also the function of time, and psi is also the function of time. So this is how the inductance is defined. Okay, now to find the, so we have the basic equation, v of t is equal to L into di of t over dt, and you can find the I of t as 1 over L into v of t dt.
Integral of
Okay, integral. Okay, and you can integrate, it's the same thing like the limit minus infinity to t. Okay, this is minus infinity to t. Because we are considering minus infinity, it is because we don't want to miss anything before our t. That's why we are considering minus infinity. Okay, if you know exactly the starting, you can start from the exact starting point, but usually when we define, we will always use minus infinity to t. Okay, so the scale is like this, minus infinity, this is infinity, this is maybe 0, this may be t. So we will start from minus infinity till this point t. Okay, this is our limit for integration. Now what is the power? Can you tell me what is the power? we will talk about the power. The power in the case of inductors. Okay, in the case of inductor, we know that the power is equal to voltage into current, right?
half Li square.
Yes. No. Please don't remember something and tell me. Okay, this we will just go through the derivation first. Okay, what is power is equal to voltage into current, and what is the voltage? What is voltage is nothing but L into di over dt. So the power is equal to this voltage. I am going to substitute with this thing. That means it is nothing but L into di by dt, and there is a I here, this I, this. So I can say that it is nothing but Li into di over dt. Okay, this much volts. It's clear? Is it okay?
Yes, yes, sir.
Yes. Now we will talk about the so this is the power. So the power is equal to L into I into di over dt. You can see that if there is no changing in the current, if the current do not change, if the current is DC, if the current is DC, then di by dt will be equal to how much?
0.
will be equal I.
Yes, di by dt equal to I or 0. What is it? If current is DC, DC means current will not change. If DC means constant, what is the differential of a constant?
0.
0.
Not
Zero.
change.
Yes. If the current through the inductor does not change, what will be the power then?
0.
Yes, this you should not forget. So if you pass a constant DC, after a long time, there won't be any.
It will be like a straight, just like a conductor, right, doctor? There will not be
Yes, it
any,
will be like a conductor. Yeah, it will not take any power. Okay, it will not take any power. Or if it does not take any power, what is the energy?
0 also.
0 also.
No. That is what I want to tell you. It will not take any power. Power means it will not do any work, right? Power means what? Rate of change of work, right?
Yes.
If you are not doing any work, does it mean that you have no energy?
Oh, no. It's not.
It means that you are not using your energy, right? You are not using your
Right.
energy. Right. Yes.
Right.
Maybe you may be sleeping. So this guy will be sleeping, right? You can say like that, okay? So if he is sleeping, maybe he is eating, he may not be doing any work. So he may be eating, not eating anyway, we can, the power consumed will be equal to 0. The inductor will not take any power as resistance. Can you hear me?
Yes, we can.
Yes.
Yeah.
Yes.
So the resistance will eat energy, but inductor will not eat energy. It will store energy actually. So inductor will store energy and the resistance will eat energy. You have to understand this difference. Okay. Now we will calculate with the energy across the inductor. The energy across the inductor is W is nothing but, you know that the power is equal to dW by dt. That means dW is equal to P dt, right? Then what is W? Integral minus infinity to T P dt. And you know that the power across the inductor, we have already seen this, Li into di by dt, Li into di by dt. So the work is equal to, or work or energy stored in the inductor. How much energy the inductor is storing currently? That is depending upon you can see the energy stored by the inductor. This is very, very important concept that what I'm going to say. Many students don't know the clear difference between this. Energy stored by the inductor is equal to integral of minus infinity to t p dt, which is equal to integral minus infinity to t. Power is Li into di by dt. So you can say it is nothing but, you can cancel this thing. So this is equal to integral minus infinity to t L into I into di, which is equal to what is this?
Li square by 2.
Yes, this you cannot integrate like this because my limit is t and I am not integrating with respect to t. You can what it will be? You can imagine like this. It will be
constant.
yes, you can say the integration, okay, not constant. You can say the integration in a different way. Okay, I will just remove this.
You integrate with respect to current, doctor.
Sorry, just sorry, 1 second. Yes, dt. Or I can say like this. Is it equal to, shall I write something like this? This is equal to, limit is there already. Okay, this is equal to integral minus infinity to t d by dt of half of Li square of t into dt. What it is? If I'm
What if it became like this?
yes, we can write like this. So this is nothing but, then what will be the integral? The integral will be half into Li square. So I can say that the work is equal to half into L into I of t the square. So this is what the integral become. So if you integrate something, now you are integrating, you can see here, half of Li square. So this is the integral. You can say that the amount of energy stored in the inductor, okay, this I am using L also because it is the energy stored in the inductor. L is for inductance. So this is nothing but half of Li square of t, and it is depending only on, it depends only on the current at present time. That means it is depend only on I of t, right? It is depending upon I of t. It is not depending upon the current in the previous time. Is it clear to you? That's what I want to tell you.
Yes.
Yes, yes.
If you take, yes, if you take a current, if you have a inductor at time t equal to 0, the current was I of t, I of 0, maybe I of 0. This is very, very important thing. I don't know whether you have understood it. This is, suppose I of 0 was 2 ampere, then t equal to 1 second, t is equal to 1 second, sorry, this is 0 second, then this is 1 second means you have I of 1 equal to maybe 3 ampere. At t equal to 10 seconds, then I of 10 is equal to maybe some 9 ampere. Then the energy at time t equal to 0 will be depending upon this 2 ampere. The energy at time t equal to 1 second will depend only on the current at only on the current at that time. That means 3 ampere. Energy at time t equal to 10 second will depend only on 9 ampere. It will not depend upon the previous current. You understood? So if you have an inductor with current flowing through it, then the energy inside that inductor, or we can say the energy stored by that inductor, will depend only on that current, not the previous current. But if you take the resistance, the total energy eaten by the resistance, the total energy that has been eaten by the resistance will depend upon where it is. Okay, the total energy that has been eaten by the resistance, actually it contains an integral, and this integral is denoting the total energy eaten by the resistance. Actually it depends upon all the previous and the present till the present, from all the previous till the present. But the energy stored by the inductor, this is the energy stored by the inductor. We are talking about the energy stored by the inductor. The energy stored by the inductor will depend upon only on the current through that inductor at the present time. Currently, how much current is flowing through the inductor, that will be, the energy will be according to it. Is it clear to you?
Yes, sir.
Yeah. So
Yes.
There will
this
be
is
energy. It was DC current.
so if DC current, yes, energy will be there. That's what I will say. I will tell you that one. Okay, we will come to
Oh,
that.
doctor.
So I will tell you, energy stored by inductor will depend only on I of t. That means energy stored by the inductor at time t, at time t will depend only on I of t. So not the previous. Okay, so it will not depend upon the previous current. Then you may have doubt that why. Okay, I think I exceed the 100 pages here. Inshallah, I will open one more thing. Okay, just wait. Okay, 1 second. Okay, so the energy stored by the inductor, that means the energy stored by the inductor, we can say the work energy stored by the inductor is half L into I of t the square. And what is the power? The power is L into I
in the I by
dt. Now, if you pass a DC, if you pass a DC through inductor, what is the power consumed? What is the power? Maybe if you talk about the power, yes, the power is equal to 0. I told you, because in DC, di by dt is equal to 0 and the power equal to 0. Is clear? Then you may have a confusion. Power is the rate of change of energy. You should know this definition. Rate of change of energy. It means that power equal to 0 means that the inductor is not giving energy to anybody, or it is not taking energy from the source. Is it clear?
the energy
Yes,
doesn't
doctor.
change in the.
The energy in the inductor is not changing. You see here,
Yes.
L into, if it is a DC, the current will be I, just I. It will not change, right? So
Right.
if the energy is suppose 30 joules, it will be always 30 joules if the current is
30 joules.
DC. If the current is DC, it will not change. If you have lot of money, just imagine like this, you have 100 real. You are not going to give to anybody, or you are not going to take money from your friend. Then you will be always having 100 real, right?
Yes.
Do you understand the point what I'm saying? You assume
Yes.
that
Yes.
you have 100 real in your hand, and you are not going to anybody, or you are not going to take money from anybody. Okay, so you will be always having 100 real. That means you are not giving the power or you are not taking the power. So the power, the rate of change of energy, how much energy is changing in 1 second, that will be equal to 0, because you are always having 30 joules and you are satisfied with that. Is it clear?
Yes, yes. Yes, doctor.
So the power means the rate of change of energy. That means the inductor is not taking the energy or inductor is not giving the energy to anybody. So if you have a voltage source DC like this, maybe 10 volt, and if you have a resistance here, control the current, otherwise your inductor coil will heat and it will damage. Let's say this is 10 ohm. Then after a long time, I'm not talking about when the switch is closed. Suppose you have a switch here, you closed at time t equal to 0. Whenever you try to close a switch, there is a rate of change. There is a change in the current, because the current is changing from 0 to a maximum. It's trying to change. Okay, that we will talk in another situation, not now. After a long time, you close the switch at t equal to 0. That means after a long time, we can say t tends to infinity. What will be the current?
The inductor will act as a wire.
Yes, inductor will act as a wire. The inductor will act as a wire and the current will be equal to 10 by 10, which is equal to 1 ampere, right?
Yes.
Now, suppose this L, inductance L is 1 Henry, then what will be the energy stored in the inductor? Energy
After a
stored
long
in the
time?
inductor. Yes, after a long time, as t tends to
Half.
infinity, you can say. It is
0.5.
half, yes, Li square, right? It is nothing but half in this case. So how much joules? This much joules. It will store half joules now. That
Yes.
means that the inductor is always having half joules. This guy is now having half joules. That means you have a current and you have a current which is flowing like this, and your inductor is having the magnetic flux which is pointing down. If the current is moving in clockwise, okay, if the current is moving in clockwise direction and going down, then definitely you have a flux, and this will be north pole and this will be south pole, and you can see the flux will be like this. It will be like this. So it will be completely flux from north to south, right? There will be a lot of flux, and this flux is maximum. That means now inductor is storing an maximum energy of half joules. So the inductor is storing energy in the form of magnetic field. Since the current is not changing, the magnetic field is also not changing, and the magnetic field is constant, because you are giving a DC supply and you are observing at a time after a long time. That means t tends to infinity. So the magnetic field is always constant. Since the magnetic field is constant, it is not changing. That means it is having half joules. It is not taking any energy. It is storing that energy like that. It is not consuming an energy, and the flux is not changing. That means that he is not releasing the energy. So he is not releasing the energy, or he is not taking the energy anymore. The flux is constant, maximum. Do you get the point what I'm saying?
Does it
Yes,
have
doctor,
electric
yes.
field, doctor?
Yes.
Yes.
So if the flux is not changing, the inductor will not consume, inductor will not eat any power. It will not take any power, or it will not give any power. He is already having half joules. He will not take any power, or he will not lose any power. That's what. Okay, that's why the power is equal to 0. The power consumed by the inductor is equal to 0. That means inductor is not doing any work. He is just acting like a wire. That's why you always study it like this. When after a long time, inductor will act like a short circuit. Act as short circuit. What is the property of a short circuit? A short circuit will never take any power, right? Just act like a short circuit. Just a conductor. Any doubt? If you can ask me. We will stop with this.
Victor, why it will act right? It will act like a short circuit after a long time.
After a long time, it is not consuming any power. You see here, if you have a resistance R, it will consume some power. If you have a short circuit, what is the power consumed?
0.
0. Since the inductor does not consume any power, if the inductor does not consume any power, if you give DC and if the time tends to infinity, you can say, after stabilizing, there will be the field across the inductor, throughout the inductor, and the energy will be fixed. It will not change. So it will not give energy to anybody, or it will not take the energy. So the power equal to 0. So that means this is equivalent, almost the same like a short circuit. Okay.
Oh. So it reaches to the maximum current.
It doesn't mean
it reaches the maximum current.
It
that
doesn't
is
mean
equals V over R.
Yes, it will reach the maximum current. Then it will act like a short circuit. It is not a short circuit actually. It acts like a short circuit. That's what I'm saying.
Yes.
Actually, this inductor is having act like a short circuit, but this guy is having energy inside it. It is having energy which is stored.
But it doesn't give it to anyone.
He will not give to anyone. But when the current changes, he will change the energy. You understood?
Yes.
So if it changes the energy, then there will be some power. That power change. That means energy. If energy changes, then there will be definitely.
Power
it is
change.
Yes. Power will also come. That means it will do some work. Sometimes energy, it will take energy, absorb energy. Okay. Sometimes it will absorb energy, or sometimes it will release energy. It will depend upon the other things in the circuit. Okay.
Yes.
Suppose you change this guy 10 ohms. You change this guy 10 ohms to 5 ohms. Then what will happen? The current will try to
increase.
When the current increases in the positive direction, what will happen to the energy? The energy will also increase, right? Yes. Now, if you increase this guy from 10 ohms to 20 ohms, the current will decrease. When the current decreases, it will release the energy.
Yes.
It will try to reduce the energy. The magnetic fields will come down. You understood?
Yes, that's it.
The strength of the magnetic.
Does it have electric field or only a magnetic field?
In the case of DC, I told you there is no electric field outside the conductor, but definitely there is electric field inside the conductor. There is no electric field outside. Don't forget these concepts. Okay, everything is related. That's why. Okay, we stop with this. In the next lecture, inshallah, we will talk about the capacitor. Let me check one more thing. Okay, just sorry, one more thing. I forgot one more thing. Okay, this the psi I characteristics of this. You know that this psi equal to Li. So I can plot like this, like the resistance. This is the current, and this is the flux linked with the inductor. This is linear. You can see this is linear. So this is a straight line. Okay, and what is the slope?
L.
What is this?
One.
Yes. Slope.
L.
Slope is L. Yes, exactly like the resistance property. For the resistance, you know, this is I, this is V, and the slope is R. This is the for resistance. But for inductor, it is like this. Now, the property, this is the first quadrant, second quadrant, this is the third quadrant, and this is the fourth quadrant. So this is a straight line. So it is linear, and it is having the characteristics on both sides. That means if this is positive, this is also positive. When this is negative, when I is negative, the flux is also negative. That means it is bilateral. I told you this one, this terminology. This is very, very important. This is bilateral. Then this is a passive. It cannot generate any energy, right? It can store the energy. Okay, so that's why, yeah, it consumes the energy. Okay, consume means it will not eat the energy like resistance. It can store the energy.
Yes.
But it is not like an amplifier. I will tell you that you might have heard. Yeah, you have already gone through the course, my course, like Handas Electronia, right?
Right.
We have seen the amplifier. Amplifier will work in active region. That's why it is an active circuit. But this guy actually consumes the energy, cannot produce the and transfer the energy in another way. That's why it is a passive network. Okay, and the property will not change with time, like resistance. If the temperature is constant, it will not change with time. So it is time invariant. Got it? Like the resistance, everything is same like the resistance. Yeah, the properties, everything is same like the resistance. Okay, so these are the properties. Inshallah, in the next lecture.
What does it mean?
Sorry, time invariant means
Time
the character. Suppose you take a inductor. Okay. Suppose you take an inductor. What is this time invariant? You take an inductor which is having an inductance of 1 Henry.
Okay.
So the characteristics may be like this, right? The slope is 1, right?
Yes.
Yes, I say. Now you take the same inductor after 100 years. After 100 years, okay. What will be the inductance? If nothing happens to it, it will be same. That means its property is not changing with the time. That's not a time invariant. It's clear?
Yes.
So if it is time changing, what will happen to the slope? Slope also will change, right? If it change, yes.
Right.
But if does not change means if it is time invariant, that the slope will be same. If it is, now you see here the slope is, the slope is 1. After 100 years also the slope will be 1. That means its characteristics will not change with time. That means, yes, the characteristics will never change. Never change with time. It's clear? Inshallah, we will see the other parts. Okay, we will see the other things in the next lecture, like the capacitor. Okay, inshallah, we will see the capacitor and we will see the sources. After that, we will start the Kirchhoff loop, inshallah. Okay, and we will analyze the network, mesh analysis, loop analysis, everything will come in the next week, inshallah. Okay.
Inshallah. Thank you so much, Doctor. Thank you so much.
Okay, thank you. Assalamu alaikum.
وعليكم السلام.
Walaikum salam.
عليكم السلام.